In group theory, when one starts to study the notion of normal subgroups of a group, one of the most important examples that one has to keep in mind always are kernels. So kernels, the kernel of a morphism of group, is always a normal group. And this fact is very, very important and very useful. It can be very useful also when one has a given subgroup and wants to prove that it's a normal, and maybe the direct approach of showing the invariant and the invariance under conjugation of elements is not always the easiest. But if one manages to realize this group as a kernel, then one knows for sure that this is a normal group. So let's now give a proof, a simple proof of this fact. So the setting is the following: f, say from some group G prime to another group G, is a group morphism. And then we know that the kernel of f is a normal subgroup of G prime. So this is the statement I want to prove. Now, first recall a couple of very basic but fundamental things to know. First is that a group morphism always sends the identity element into the identity element. So let me give a name. I will, for simplicity, I will just call the identity here 1 prime and the identity of G 1. So f of 1 prime is equal to 1. Moreover, f of G, so the inverse of this element, so the inverse, so to speak, passes inside the brackets, and this is f of the inverse of G. So why is this so? For 1, we can, for example, write f of 1 prime as f of 1 prime times 1 prime, so the identity element times itself, and this then apply the definition that f is a homomorphism. So this has to be written as f of 1 prime times f of 1 prime. So what we have here on the left and right hand side is an element here in G, let's call it y, and an element, and on the right hand side we have y squared. And of course the equation y equals to y squared is equivalent to 1 equals to y. So now for 2, I will apply the fact that from point 1, from part 1, we can write 1, the identity in G, as f of 1 prime. And so for our G, for any G, this is G times G minus 1. And by the fact that f is an homomorphism, I can write this as fg times f of G minus 1. Now you see that if I multiply here on the left this 1 by the element f of G inverse, and then on the right hand side of this I can cancel this and I have my statement. So now let's prove that the kernel is a normal subgroup. That is, we have to show that kernel of f is invariant by conjugation. that is G times ker F times G minus 1 for any element G is equal to kernel of F. Okay, so let's do this. Let's observe that if we pick an element X in the kernel, then by definition of the kernel, f of x is equal to 1, right? So now we can observe, we can note that g, so our condition that gx, g minus 1 is in the kernel, is equivalent to having f of this element equal to 1. Now, since f is an homomorphism, I can rewrite here as f of g times f of x times f of g minus 1, which we know by the previous observation is f of g minus 1 inverse. So this is equivalent to this identity. Now, equivalently, if I multiply this previous identity here on the left by f of g minus 1 and on the right by f of g, I can rewrite this as saying that f of x has to be equal to f of g inverse times f of g, which of course is equal to 1. Therefore, this precisely happens if and only if f of x, x is in the kernel. So our two conditions here are indeed equivalent. So this shows that the kernel of a group morphism is always a normal subgroup.